Hello and welcome to this series on compiler design. In this first installment, I'm going to talk about Foo, which is a small project I've started. And the idea is that every new element of this series, I'm going to talk about a new stage or a new part of the compiler. Foo is already in a state where it can parse things and make sense somehow of those things. But for the purpose of these videos, I'm going to start over in a develop branch, and in this develop branch I'm going to slowly at every video add more content that corresponds to the content of the video, then tag them hopefully. So I'll start in this video by talking about the basics. So Foo is a functional language, hence the name Foo. It's not meant as an insult. In fact, it's more of a reference to Dr. Fu Manchu in the book series, if you know about that. But anyway, the point is that it's a small compiler for a functional language, and this compiler that we're going to work on is written in C. So in C, there's a lot of infrastructure that you need to start with, in particular with respect to data structures. So I'm going to talk a little bit about that before going to the main topic, which will be about Lexing. So first of all, we need to have a build system, and for this I'm going to use CMake. If you look at this folder structure here, we have two CMake lists, and the root one contains essentially only those 4 lines, which basically instructs CMake to create a project and enter the subdirectory src in which the other CMake file exists, which then creates the executable foo, then set up include directories and set some properties. In particular, we want to use the C11 standard and disable C extensions, among other things, and also use the math library. So for instance, if we want to use sine and cosine, we need to link against the math library on Linux. So this is how we do it in this CMake lists file. Now we also have other things, of course, already ready that I left in this develop branch. There's a set of data structures and basic things which I've left in the core directory. These basic functionality, or this basic, set of functions, is just very simple. So there's things to perform hashing if you need to hash your objects. So you can hash integers or pointers or strings, things like that. There's allocation functions, which are here to replace malloc, calloc, and realloc. But as the name suggests, they just crash with a message if they cannot allocate memory. This is to essentially prevent reading from a null pointer. Not really important, but it's nice to have. I don't expect this to happen in practice though, so again, it's not really relevant. You could just leave by calling malloc directly here. Then there's a small but interesting formatting tool which allows us to replace printf. That's really nice, because in a compiler there's a lot of things you might want to do, and in particular error messages require you to present things oftentimes in colors or with a different style. So here we have essentially some formatting function which allows us to format strings and then print them with NC terminal codes so that they appear with colors or with a certain style in your terminal. The idea is that we have a format function which takes a format state and then a format string which specifies commands a bit in the style of printf but different, and then format arguments, which are one of these things, which can specify style, of course, if you want to change the current style. So basically you can print all these things, and it's really practical, in particular for error messages. Anyway, at this point there's also other data structures that are worth mentioning. So there's a memory pool. Everyone knows what a memory pool is, so I don't think I have to explain what that is. There's a string pool, which is again a pool of strings. The reason why this thing is interesting, let's put it like this, is that with a string pool we can make string comparison much faster. Because now if you have 2 strings in a string pool, then they compare equal if their pointer or their address is equal. So that's a really nice property, but also it makes the compiler save on memory when creating strings, which is a nice thing to have. We have this hash table that I mentioned earlier. Again, it's a standard linear probing hash table, nothing really fancy here. There's some logging mechanism, which is important if you want to show errors again. So I defined a couple of things that are interesting here. So a file position with a row and column, which is just like what's shown here in Vim. So you can see there's the line and column number here indicated there. So that's exactly what we record here. And the byte offset is the position in the file, the number of bytes that have been read so far before reaching this position in the file, essentially. And the file location is a file name along with two markers, one for the beginning and one for the end, which correspond to the position, to the location considered. So essentially a location is something like this. It's a range with a beginning and end. So that's basically it. And yeah, so these functions can take a location, and hopefully the idea is that you can print a diagnostic, so you can print, you know, these nice error messages that Clang produces, where you have a little arrow in the terminal that shows where the error is, because you know where the error exactly happens within the file. So you can literally just write symbols under the part of the file which contains the error. Other data structures, well, we have some UTF-8 related things. So again, it's utilities mostly just to be able to understand how to decode UTF-8 strings. Now that we have this, the first thing we're going to have to do is to create a main function, which I'm going to do right now. So I'm going to do this like this, src, and then I'm going to call this driver, maybe driver, and then main.c. That's it. And there I'm going to say, well, I have a function and I return 0. Wowee. So we have essentially the entry point. This is not really interesting. Okay, the file doesn't exist. So I create a window and there I make a directory. I see it remembers the name. And that's it. I have my file. I need to add it to the CMake files. And here we go. And I can create a build directory, do this, and then do that to run CMake, then say configure generate. And of course cannot find the file, it's fine. I'll probably mistype something. If I go back here, you see I forgot to call this proper name. Do it again. Oopsie. And there we go. So this is because I probably forgot to remove old stuff from the master branch. So the previous branch had the full thing with already some stuff implemented, but I've removed it. So I need to remove it. Actually, you also notice this IO here has no reason to be in here. Just like this type in AST, we don't have them, there's no type. And yeah, we also need to change the C file that goes with it. So to do that, we're going to have to remove this here. And maybe, oopsie, not really helpful. So I remember that at some point I printed the types and I need to remove this as well. Alright, so it is somewhere around here, exactly here, print type. Anyway, alright, here we are. So now we have our file. I can just do bin foo. Nothing happens, that's what we wanted. Now we need to read a file, and to read a file we can write a small function to read a file, obviously. To this end I'm going to reuse the old source code. I don't want to code this myself. So here goes. Alright, that was painful. So from here I can just read the file, I suppose. Exactly. So this function here just reads the file. I'm just gonna delete it, that would be a bit too aggressive. So here goes. We have a function that reads a file, and it takes the file name to read and returns the file size, but through a pointer parameter, and returns the actual file data as a return value. It uses the standard C library to read the file, so I need to include it, of course. Here goes. And of course in C you don't have Boolean types, so you need to, well, by default at least, so you need to include a cdebool to have the standard bool type and false and true defined. Then you of course also need to include other stuff such as stdlib.h to get free, and malloc, and finally we need to include this alloc library that I use because I use realloc or die. Alright, so that's it, and now I can do make. Great. As you can see here, I still have the problem that my linter called ale in Vim reports an error. I want to fix this by saying that I want to export compile commands, and then I can just remake, and I can do start Vim. It should work now. Exactly. So now it says unused function read file, which is a correct error message, I would say. Alright, so what's important to see in this function is that we just open the file, then we read the file data via essentially chunks of data, and then if there's an error in the process, we close the file and free the data, return null. If there's no error, then we reallocate the data with some chunk size and continue reading like that. And then every time we read something, we multiply the chunk size by 2 so that we read even more next time. Finally, we close the file, and importantly, we add a terminator, not the character from the movie Terminator, but null terminator to the string, which essentially allows us to use standard C library functions like strtod or strtof, or all these string to integer, string to floating point value stuff, which is really important because the spec doesn't say anything about non-terminating strings. So at this point we want to read the file, so we're going to say, hey, we need arguments here. Then from here we're going to read those files, so we're going to assume this is the first one. We're going to do so we have our file data. Now the thing is, what do we do with it, right? At this point we need to lex it, which is transform this stream of bytes into a stream of tokens. So first off, what's a token? Well, a token is some word in the very simple sense. It's, in the programming language, some element that the parser is going to deal with, but at the point of this explanation, I think it makes sense to see this as a word like as in a word in English, for instance, where you see a word in a sentence. So a token just agglomerates characters together to form words, and of course you may have symbols in between words, so a token can also be a symbol. So let's write this. We're going to essentially create another file which we're going to call token.h. We're going to go here and say I have a directory called lang because language, and then we call that token.h. Usual stuff, we create these guards. And at that point, we need to create the structure of a token. So what's a token exactly? Well, a token, like I said, should probably be a structure. In there, what do we want? Well, we want the position in the file. I already mentioned that before, but the position is a file lock. Then we also want to say that there are different types of tokens. Some tokens will be identifiers, for instance, like names of things. Some tokens will be keywords, like if, else, this type of stuff. And some tokens will be symbols, right? And also some tokens will be literals, like string literals or character literals or integer literals, you know, that kind of jazz. So at that point, it makes sense to introduce a tag. So we're going to call it a token tag. And what's in there, right? Well, what I said just before, but you know, there's a clever way to create lists. You can create lists here by just listing your stuff by doing A, B, C, D. That's one way to do things. But let's say I need to associate data with A, B, and C, and D. Now I would have to write a switch statement somewhere in the function to do that kind of mapping between A and, for instance, a string containing A, if I want to stringify the elements of the enumeration. So that's kind of bad, right? Instead, what I can do is something like this. Here, I can essentially create a list of things, and every element of the list, I'm going to pass to a function f. And this function f, or this macro f, can do whatever they want with the data. So I do this, and I say, for instance, let's say I have a literal. That's what we talked about before. Let's be even more precise. Let's say it's an integer literal, okay? And then I want a string to say, well, it's some kind of integer literal. Integer literal. All right. Do the same for float. Something like that. Maybe car literal. Maybe a string literal. Maybe of course we change this to that. This is string. Very good. So at that point I may want to also add identifiers. So this is an identifier. And maybe I want to have a list of keywords. So let's do this like that. Another list, keyword list, and we're going to pass all the keywords to f as well. And at this point, we can't write the file, of course, so I'm going to create the directory. Let's go back here. nkdir src lang should be enough. Do that to build, and from here I can probably write now exactly. Note that we need the file location structure, which is in the log, so that comes with the log, exactly. And it's not found because we haven't updated the build commands.json file, but it's for later. Right now we don't do any of that. Define keyword list f. So we're going to create a couple of keywords like if, right? It's just if. And else, of course, goes with it, hand in hand with if, and so on and so forth. Let's just do this kind of list. I think it's enough. We have enough to display the general idea. And then we're going to do, of course, token list with maybe f. Problem is we don't have f at this point, so we need to create an f we're happy with. Define f. And f takes a name and a string. And here we're going to do token underscore dash dash name. And that means we take token, we concatenate it with name, and then we add a comma. And that basically will go through the entire list every time adding the first thing here, the name, if, else, or ident, or int, literal, and all these things to token, and therefore creating the enumeration value. So that's all we really need at this point. I can even be, a bit aggressive and do something like static const car get or token to string, and I can do token tag. So this is cool, but as you can see, one of the problems is that we're redefining things every time. So for safety, we can always do this. Undefine the macro that we just defined before. Something that's kind of important if you do this several times in the same file. All right, but that's not enough. So we have outlined what a token looks like, which is pretty cool, but still not enough because we also need a couple of symbols, right? So let's create a couple of them. Right, that's something. So we have something to work with here. And well, at this point I can say I'm happy, but in practice though, we still don't know a lot about what we're dealing with here. So what I'm going to do is I'm going to write something that actually takes the string that we just read from the file, this file data, and I'm going to transform this into a stream of tokens. The idea is that we're going to write a small function which is going to take the current state of the Lexer, which will be essentially just a pointer within the data, and it will increment or move that pointer, read whatever comes, and turn that set of characters that it sees into either token or symbol, essentially moving along the stream of bytes. So we're not going to do this in token.h, we're going to need another file for this, which I'm going to call lexer.c. src lang lexer.c. Well, let's start with h, right? Give you an idea. All right, so here we just do core. We're going to do something like struct token, events Lexer, struct Lexer, Lexer. That's our struct Lexer. It's just a struct which contains, first of all, a current position. So struct file pos, right? That's the position. Then it contains also something like file name. I don't think the file position has a name in it. As you can see, it's only in the location. So we add the name here, then we do maybe use something like that. It's the file data. So it's t. That's the current byte offset within that data. And well, I think that's pretty much it for the moment. Then we want to create a Lexer. And we create it from file data and the size. Maybe I could also add the file name. Alright. Also, we need something to destroy the Lexer, because right now we don't allocate data, but maybe later on we will. In fact, I know for sure that we will, but we can account for this right now. Alright, very nice. So, alright, that's our Lexer. Then create an implementation for it. Very nice. So now that I've done this, I might want to do something like calling the Lexer here. So struct Lexer, new Lexer with the name. We can do this like this. static void compile file const file name. Let's type this, of course. And we do this, take the file name here. Okay, pretty cool. Now we can compile it. Maybe I can even return some boolean code here. So we do return compile file. Did it work? Yes, return 0, otherwise return 1. Okay. And now I want to include the Lexer stuff. So the Lexer stuff lives in Lexer.h. And we forgot to return a value, so we return true. Very nice. So here this indicates that we have errors in this file. I can have a look. And it says unused function, really important. Okay, so here I can start coding the Lexer. Here I just need to return a Lexer structure, so that's what I'm going to do. Let's be consistent here, it's important. It's also important to say what size it is, because we could be talking about something different, you know, like the size of... Actually, we don't need the file size at this point, do we? I don't think we do. So I could... let's just keep it in, okay? And if we don't need it, we'll remove it. Size t, file size. Oh, so here we go. Everything that's not in this list is going to be zeroed out, so byte offset is going to be set to 0, file pass is going to be set to 0. Maybe I want to set it to 1, because usually row and column numbers start with 1, so that's what I'm going to do. File pass equals get, or I can just do it. Row 1, column 1, byte offset is 0. Right, that's Lexer, initialize. And here we do Lexer, here we say void Lexer, because we don't use it, but we don't want any warning. Maybe I to do, because we're going to have to do things later on. And advanced Lexer, that's the interesting stuff coming on. Coming in, well, no way. Anyway, so that's our Lexer. We advance it. To advance it, what we really want to do is to read the next thing, and if the next thing, say, is a symbol, then we're going to return that symbol. So for that, I'm going to write small happy functions. Static bool accept char. That's going to accept the character if the character that we provide is the same as the one in the stream. Insert char c. Sorry for that. And if Lexer file data. Oh, before that we could have a small function to help us access the current car. Get cur car. Struct Lexer. Maybe it's not so difficult to type. We'll also make it const because we're not going to change anything here. So return Lexer arrow file data Lexer byte offset. Static bool is if reached const struct. So Lexer, that's going to tell us when we reach the end of this stream. Okay. Oopsie, Lexer arrow file size equals Lexer. Is it called file pass or pass? Yeah, it's called pass. So let's call it file pass, I guess, for consistency. So it goes. So if the byte offset is equal to the file size, we've reached the end of the stream. Now, if we do something like this, we cannot be at the end of the stream. So let's write this as an assertion, because it's simpler, and then later on we can write the code in such a way that we never call accept car if we already are at the end of the stream, because that would be stupid. So at this point I just test that we are not at the end. Of course we're going to need the assertion. Standard library stuff. At this point we look at the file data, and if the file data at the current position is the character that we're looking for, then we accept it. Get car Lexer equals C. Here we're going to get the next character, so that will be like skip car Lexer. We skip the current character and return true. Else we return false. We need the function that skips the current character, so we're going to do static void skip car struct Lexer. What this does is just moving the current pointer. I could re-implement this by hand, but it's a bit annoying because I need to look at the UTF-8 meaning and all this stuff, how I implemented the UTF-8 support. I mean, the general idea here is ideally, in a world where things are very simple, you would just do something like Lexer arrow byte offset or file plus the byte offset plus. That's all you would have to do. But in the real world, unfortunately, things are not that simple because you need to handle UTF-8 and things like that. I want to handle UTF-8 because I want to be able to write strings that contain characters, and I want that to not break the way I show error messages. So for that to work, I need to have essentially the accurate position in the source file and not just column numbers that correspond to, you know, the bytes in the file. Because if I do, for instance, something like this, okay, let's try again. Okay, this is a U or umlaut, as in German, if you know a bit of German. Then this character here is UTF-8. If you see, what happens here is we have Vim telling me it's either 14 or 13, depending on who you are. Because before it were 12, but after it, it's either 2 bytes or 1, depending on if you're interested on the number of bytes or if you're interested in the number of characters. Personally, I don't really know what's best. I think most editors would return the number of characters. In this case, there's only 1, but the problem with UTF-8 is that you can't really count characters. Sometimes you have stuff that's not a character. Sometimes you have bytes that do not correspond to any character. Sometimes it's just unclear what a character is. You can count, of course, code points, but is it really relevant? Is it really what you want to look at here? I don't know. So essentially, maybe we just forget about UTF-8 for a moment and just say, we just leave it like that and increment the offset. For a second, I thought we would probably be better off by just trying to be clever with UTF-8, but maybe I just leave it like this, and then later on, if I need to add UTF-8 back, I'll do that. Let's start with like this. I think it's saner. So now, how do we implement the Lexer? Well, we have all the basic bits. I think you can just do if accept car Lexer. And if we accept, for instance, an open parenthesis, right? Now we're going to return a token Lexer, and I want to create a token that is a parenthesis. So I think it was called token L parent, something like that. Of course, we're going to need the position. So I'm going to do this. This is going to be a function that takes the Lexer, the beginning position, and the tag, and it's going to create a token for me. The reason I need the beginning here is because accept car moves the pointer, as you can see here. It moves it. Of course, it should also move the row and column, which I'm going to do right now. So Lexer file pass dot row plus plus if get current car equals that. Then we move the column or the row, yes, the row. And then we have to reset the column row. Otherwise, I guess we just have, we just have to increment the column number. Nice. So that's all we need, I think. Then here I can just do struct file plus begin is equal to the current position. And yeah, that's pretty much it. I'm going to fix this as well because this is annoying for linting. I need to have the information about the why there are errors, and here I can't see anything because the include file is missing. So I'm going to regenerate this. Oh, but I forgot to change the CMake file, so let me just do that again. Lang lexer.c. That's the only C file we added, like that. Like, of course I have errors, but maybe now I see things differently. Exactly. So here we need to pass Lexer. Oops. And here we're going to need to talk about make token, or token, sorry, wrong pronunciation here. Static struct token make token. Okay. Alright, and then the position would then be essentially the location between the begin and the end. So we're going to do, well, first of all, I'm going to look again at this. It's called file lock lock. Maybe I call this file lock. Maybe I call this file lock lock. Ah, file lock makes sense. Let's call this file lock. File lock equals dot begin. Well, it's begin, right? And dot end is Lexer file plus. We also need to set the file name, so I'm going to do file name equals Lexer file name. There goes this entire structure. And is that it? Is that it? I need to set the tag and file location. There's no other data for the moment, time being. So token L parent doesn't exist for some reason. Use of undeclared identifier. Before I do this, I want to also return something in the case where we don't have anything meaningful. The make token Lexer begin, and I will call this token error or token invalid. Token error makes sense. And log error. That's also something we need. So you see, the log is something that helps me printing error messages. I have a location for it, I have the message, but I don't have a log object, right? So I need to put this into my Lexer. I'm going to say I need a log object, so I'm going to struct log log. And of course, I don't have definition for it, so I'll do this and log. I think it's clear that calling this log doesn't really help, so I'm not adding the name here. Alright, so how do you create a log? You need a format state and other stuff. So if I look at format state, how do you create a format state? I don't know how you create a format state. Bad. It's really bad. I should document my own code. I feel now ashamed slightly. So struct log equals state equals. So I can set those two things to null. I think that's fine. Ignore style should be false. Indent should be 0 and tab should be a set of characters. So I can just do the tab equals 1, 2, 3, 4. Right. Nice. So we have a log object and I'm logging on it. Of course, I also need to print the error messages after they've been essentially written in the log. To do that, I need to use the state and do something like print format buffs and free format buffs. print format buffs just prints the contents of the log. So I do log.state, I think. Is it? Maybe. And file should be std out. Okay, and free format buffs log state first. Right? Or we can do log.error count is 0. There we go. Very nice. So log error. Now I can do Lexer error log, and I can write a message at the current position. The current position though is, and that's one of the issues I have, that we need to eat the current thing, and then, because if we don't, so here at this point we are looking at something that we haven't yet eaten. We haven't yet eaten the next characters that come. So at this point I need to eat them, and that will change the current position in the stream. Then I can emit an error message at that proper position. To do that, I'm going to essentially move this line just here and do a struct token. And this error token is even better. And I'm going to do skip car Lexer to say that I eat whatever comes next. And now my error token has the proper location. Error token dot lock called file lock. Oops. Unknown token. And I don't have any parameters yet. Maybe you want to show what is contained inside this token. But at this point, I think it's too early and I don't want to do this. So I'm going to leave it like that. You're just going to have your error message as raw as it comes. That's basically your advanced Lexer function. Of course, at this point, we're not treating empty space and things like that, but we're doing pretty good as far as I know, because we already pretty much have everything we need. So advanced Lexer is almost working. We just have a problem with somehow the token is not existing. So I'm going to import this file. Has it fixed anything? No, but as we can see, we are getting somewhere because token is already defined somewhere. So we have token underscore name, we have L parent. Maybe that's because it cannot. Let's fix this first. Token L parent. Let me see if I get something more interesting. No, I still don't get any meaningful information. Maybe if well, let's first create the error token. F error. Or invalid token, maybe something. Invalid token is a good definition of what an error is. Did it fix one? Yes. So it's just L parent that doesn't exist. Must be something pretty stupid. Yes, it is pretty stupid. It's because I haven't done this. And there we go. How's this? I can do the other one, this one for instance. And also we're going to need one to represent the state where the Lexer has read everything. So I'm going to do, no, not here, eoff, which stands for end of file. Nice. And with that, I can oops, sorry for this is pretty bad. At this point, when I reach the end of the stream, I can output this special token which says, hey, this is the end of the data that I have. So if is eoff reached Lexer, return make token Lexer begin token eoff. Okay, what about empty space now, right? To do that, I'm going to do something like eat spaces or skip spaces. Maybe that's a better name for it. Lexer And that small function is gonna, well, skip spaces, as the name suggests. Static void skip spaces. Alright, so what we do is very simple. While we are not in EOF, what do we do? Well, we take the next character, and if it's a space, we skip it. I think we can use is space. I forgot to do this as well. And so while we're not at the end and the current character is a space, then I skip the current character. I'll just do this like that. And is space I think is in C type. Maybe I'm wrong, but we'll see. I think it is. Yes, it is. No longer have any warning here. So as far as I know, this is just a Lexer that parses parentheses. It's not super useful, but it's something. All right. For fun, now create a file and build. And there I'm just going to put parentheses. It's not super interesting, but you know, gets you somewhere. All right. That should pass. Seem to pass. What if I do this? Also passes. That's kind of weird, isn't it? I think I know why though. It's because we just never run the Lexer, right? So we should do while defense Lexer. Lexer, the tag is different, token EOF. Something like that. Unknown token. That's a much better, nice thing. So we have 2, 1, 2, 2, and 2, 3. That's in the second line. That's here. 2, 1, 2, 2, and 2, 3. Very nice. Very, very nice. So this is what we expected, right? We're not parsing these things properly. And now if you want to say accept identifiers, you do something like this. You do if the current character is something like underscore, or if it's a letter, right, is alpha. Well, I think we're missing this parenthesis here. We can just eat it, and then we have to look at what follows. And while what follows is a character, an underscore, or a number, we eat it. So get current car Lexer. Alright, that's basically eating the entire identifier including underscores. And now we return a token. So return make token Lexer begin token update. So these things should disappear. And indeed they do. So I guess you have a feeling for the Lexer now. The Lexer works essentially like that. It's very simple, and all it does is just parse characters as they come and reject whatever it doesn't like. It's just very simple, and all you really need is these two functions: skip car, which moves to the next character, and accept car, which just moves only if the current character is what you want. So with these two functions, you can implement your Lexer, and well, it's not too bad, right? For C code, it's still readable, it's still understandable. There's nothing very, very complex going on. And well, it will become complex as you add more things in your Lexer, but at this point, it's still okay. One last thing though is for literals and for keywords. Literals, well, I guess you get the idea. You look for digits and then you eat them as you see them, and then if you see a dot you skip it, and then if you see again digits you continue, essentially looking for the pattern of something, looking like 1.3e plus 23 for instance, or 1e 27 for instance, something like that. Could also be 1e minus 27, something like that. So essentially you look for strings like that and you accept them as you see them. But for keywords, it's a little bit trickier. So what we're going to do, and this is the reason why there's this free Lexer here, is that we're going to need a hash table. Let's call this keywords. Okay. Now we're going to do the keywords is equal to new hash table. Always forget what the prime user says. Capacity lm size. So we're going to do capacity of, I have no idea. Well, I could count the keywords, which is something easy to do. So I could do keyword count. So I can pre-allocate the exact amount of keywords I need. And the size of a keyword is obviously the size of char. That's it. Yes. So to get the number of keywords, I can do something like this. Enum. Again, we're going to use what we did before, the keyword list. And I'm going to define f name str. And this time I'm going to just say I create a new enumeration value for each called keyword underscore followed by the name of the keyword. And then I essentially put 1 per keyword, so the last one is going to be the number of keywords. So we have our number of keywords, everyone's happy. I can also include a hash table. Now that we have the hash table here, I need to fill it. So actually that's probably a bad idea to do it like that. Do it like this. Lexer, and do turn Lexer. Okay, let's add the keywords now. So I can just do I register the keywords in the hash table Lexer.keywords. Very nice. So here we register the keywords in the hash table. We do insert in the hash table, and what does it take as an argument? It takes the element to add, in which case will be a keyword. I need to create a structure for keyword. Since we're going to look at essentially a range in a string, we're going to look at two positions, right? A token is essentially just a tag plus a range in the data, right? So if I want to compare the contents of that range with what's in the hash table, the contents of the hash table have to also be in that format. So we're going to represent each keyword with two const char, or maybe a const char name and the size t number of characters essentially. So it doesn't have to be null terminated. Const char name and size t length, or length, whatever, doesn't really matter. And then here I also need to change this because now it's not correct. Okay, create a keyword, struct keyword, and we're going to say the name is of course the name, or rather the string of the keyword, and the length is going to be, well, strlen in that string. And we need the hash value, isn't it? Yes. So the hash value is just hash string of the string. And the element size, we've seen that before, it's size of struct keyword. And finally, we need a comparison function. We'll call this compare keywords. This is a bit muddy because at this point everything is just non-existent. The string does not exist. Compare keywords does not exist. Well, at least the hash table exists, but that's pretty much it. So to start, we're going to do this. Define f name str and do this. So that basically means that we can do this per keyword. So keyword list f that essentially just inserts every keyword one by one. Of course, it's still going to complain about compare keywords, but we're going to fix this really easily. Static bool compare keywords const void left const void right, and then we're going to just compare them. So return memcmp struct keyword Do we even have to? I think we do have to convert this to a struct keyword star. Left name struct keyword right and the name len. Well, the length should be something like that. Sorry, no, len. And of course, the number of elements should be the same. So let's do this too. We're going to do this like that. Simple comparison. Return this and that. All right, that was nice. So return true if the length is the same and if the two strings compare identical. For that, we're going to need, of course, string.h. All right, so that's our keyword. Oh, we also need to include, of course, the hashing functions. It still complains. Too few arguments. Yes, because hash string also takes the init. Now it's fixed. So it's in our hash table. We still have a bit of a problem here. F macro redefined. Yes, I need to do this here. Much nicer. And finally, we need to free the data. And what else? Well, here we just have to do a lookup now. If we have an identifier that is inside the set of keywords, then we know it's a keyword. If not, it's not a keyword. The question is, which keyword is it though? The answer to that is we need to put this in here. Otherwise, we won't know. So, well, maybe I could just add it here. Enum token tag. And instead of doing this, I'm going to add the tag, so it will be token name. That gives me the name of the token. Then I can just do this like that. Struct keyword is equal to find in hash table. And then from here we need to find the keyword with the name that we just parsed, or the name we've just extracted from the stream of bytes. So we do this simply by creating a keyword like this. Maybe that works. Struct keyword. So the name of the keyword is going to be whatever is in the stream at the beginning position. So that would be Lexer file data plus begin plus byte offset. That should be the position from which this entire token starts. And the length is going to be, of course, the distance between begin and the current position, so the number of characters with each insofar. So that would be Lexer plus byte offset minus begin byte offset. Alright. As for the tag, I don't think it really matters. I think we can set it to 0, so I'll leave it like that. Alright, we need the hash, so we're going to do hash string hash init, and of course I need the same pointer, and we're going to also need the size of the element, size of struct keyword, and compare keywords. It's a bit complicated, but here we are. If keyword return make token Lexer begin token keyword token. Which token is it? Well, we know that because it's inside the keyword. We do keyword tag. That's it. Very nice. We can even change this into return if we have a keyword. Return that, otherwise return that. Like this, nice. I don't know really how to simplify that. Maybe I could create a keyword separately, I don't know. This is not very nice to look at, but it should work. Or maybe not. Yes, we cannot do this because of course the hash table does not exist at this point, so we do it like that, and now it works. So the question is, does it work if I do something like if? We don't know, right? But we can just do something very simple. Before, sorry, I'm just a bit lazy here. If keyword, we're going to printf, I don't know, something like this, d, just you know, to know that in fact there's a keyword and the keyword is correct. I won't bother implementing and printing, or no, actually, I can be a little bit less stupid for once and do something like this. Get token, or is it token to string? Maybe token to string, yes. Keyword tag. And now you see that in fact it does not work. Reason for this is unknown to me yet, but we're going to see soon enough why this is the case. So register keyword should register those keywords. And right now in terms of keywords I have if and else. These are my keywords. So I insert the string, and I think I know why this does not work. It's because I'm essentially hashing the entirety of the stream every time I see a small thing. So I need to only hash the relevant part. So to do this, I'm going to compute the length here. let's do it like this. Const car length, oh, this way, name. Size t len, and we can do the same thing here. Actually, it looks nicer like this. And there we go, it worked. So the difference here is that now instead of hashing the entirety of the stream from where the token was up to the end because it looks for the null terminator, we're only going to hash the range covered by the token, which is just these two characters, the I and the F. So now that's correct, and then it finds the keyword and it prints it, which is what is to be expected here. It's not going to do it for keywords that do not exist, only for those that exist. If I do else, it should also appear. But if I do something like, I don't know, while, you don't see it here. However, the nice thing about this whole design is that if I look at my Lexer, wait a minute, no, if I look at my tokens and I see, well, I want to add a keyword, how does it work? I can just do something like while here, recompile, rerun, and bam, it exists. And that's automatic, and I didn't change the code. And if I want to add a new one, I can just do it like that, very, very simple. Let's say I want to add the keyword fun for function. Fun, because we need to bring back the fun to programming. Cool. I could call this foo, but that would be a bit weird, I would assume, for most people. And I'll have fun by adding this in the file. And it doesn't work because I haven't recompiled. But yeah, I recompiled, and now it does work. Very nice. So this is where we stand. This is how we implement a Lexer in an efficient manner. It's okay. It's not necessarily super easy to read, but it's arguably nice for C code, I would say. In terms of C code, it's still pretty readable and pretty much understandable as far as I'm concerned. The other nice aspect of this, as I said before, is that it's automatically generated. So adding new keywords is going to be automatic. The only problem is for other things like symbols. As you will see later on, you may have lots of symbols in your language, and then that's a bit tedious to have to add them every time. And particularly if you have symbols, let's say like less than, and you want to add less than equal as another symbol, so you're going to have to do something like this. Nested except cars, like this, return, make, token, Lexer, begin, token, less than, or less equal, let's do it like this, let's token less equal. And that will be like token less. This can be quite tedious because of course you may want to make that as complicated as you want, and yeah, well, that's kind of annoying. But of course it's only for symbols because everything else is handled automatically. And for, like I said, literals, it's also pretty easy. You only have to add them following the regular expression syntax that str Todd and friends understand. So str to L, str to D, str to F, all these functions, they expect something that looks like this, 1 point something for the floating point versions, but 1, and then maybe an exponent, and then plus or minus, and then some number after it. So in that sense, I think it's pretty easy to implement. So that should get pretty much the entire idea of the Lexer out. I just need to add those two symbols to the list. And it should recompile again. Less equal and just less. There we go. So that's it. I think that's it for today. I think that's pretty much already covering everything we need to know. And Next time I want to talk a bit about parsing this time. This was interesting, of course, from the point of view of software design. I think I exposed an important idea here, which is to try to auto-generate as much as possible. This register keywords here, for instance, is only possible because we have this list of keywords, which is pre-recorded in token.h. Without it, we would have had to write the list of keywords manually in there somehow, maybe with a for loop, and maybe with something like static const car keywords, something like this. But that's manual and tedious and everything, and this way of representing lists is really practical because none of this is required, and there's only one place where all these tokens appear, which is in here. So if you need to change things, change it here. Of course, you may need to change the Lexer if you touch the symbols, but other than that, it's pretty straightforward. All right. Well, thank you for your attention and see you next time.